Okay, so in this module, we're going to be talking about something different. Basically, the idea of a continuous function. What do you think a continuous function is? How do we define a continuous function? There are different ways of doing that. So far, what we know for a fact is that if you were to talk about a very conventional way of describing continuous functions, it's any function that I can draw without lifting my pen off the paper, right? Any function I can draw. If I take a break over here, then there turns out to be a hole over here between the function, right? Any function that you can draw without lifting your pen off the paper is basically a continuous function, if you think about it, in very conventional terms, right? But the idea is, what if we have very different functions that are so complex it's hard to even think about drawing them? What about sine x over x? What about tan squared of x? Tan squared of x is actually simple, but what I'm saying is, the idea is that any function that's so difficult to compute would be very difficult to graph as well. So we need to find a different way to deal with this, right? So there's this idea of function values, right, that we've talked about so far. Remember when we try to compute the limit as x approaches 4 for 3x squared plus 1? What did we do in this case? We simply plugged in a 4 because we knew that the function value would equal the limit value in this case. So what happens when that happens, right? So that's 16 times 3, that's 48 plus 1, 49. So what's this giving me? This is giving me the limit at that point, right? So the function value is equal to the limit over here, but this works only for continuous functions. Now we're going to try to define these continuous functions, right? So if we have the example over here, when sine x is divided by x, we know that we can calculate the limit of this, right? We know that the limit of sine x divided by x when x approaches 0 turns out to be 1, right? But this is problematic because, as it turns out, sine x over x is not defined at x equals 0. So the function value is not equal to 0 in this case, or any value, because it's giving me sine 0 divided by 0. That's undefined. That's clearly undefined, which means this would be a discontinuous function. Or in other words, this function might exist on values other than 0 but does not exist at 0, which means there has to be a hole at x equals 0. That's a very good way to analyze whether the function is continuous or not, because in a lot of the cases there turns out to be a discontinuity in the form of a hole, which we will look at later examples. So to define continuity, we come up with 3 rules. The first rule: the function value exists, right? And in this case it's going to be f of a. Why is it f of a? Well, it's simple, because we're basically writing the limit in a general form, right? So limit as x approaches a for f of x turns out to be L, right? The second thing, the limit as x approaches a for f of x exists. Third thing, the limit exists. This limit that we evaluated into has to be equal to f of a. This is not that hard to understand. What this is saying is, if the function is continuous, then the function value is equal to the limit value. Exactly what we did over here, if you think about it for a second. We know the function over here, it's 3x squared plus 1. We know that it approaches 4. We plug in a 4 because we know that it's a continuous function. If it weren't continuous, if it were sine x over x, and we were trying to make x close to 0, then it wouldn't be continuous. The limit would turn out to be 1, right? But the function would be discontinuous. So let's try to apply this to sine x over x. Can we do that? Think about this for a second. I have sine x over x, right? So I apply the first rule. Does f of a exist? Well, we know that if we try to plug in a 0 over here, we get sine 0 over 0, right? So it does not exist. What about the second condition? Does the limit exist? the limit as x approaches 0 for sine x divided by x. Well, yeah, it does exist, and it's equal to 1. But is 1, the thing we computed in 1, equal to the thing we computed in 2? Well, not exactly, because it says over here that it does not exist. The function value does not exist. And the limit exists, but it's equal to 1. So, does not exist does not equal 1, if we were to think about it in primitive ways, right? Which means that the function is not continuous. Right? Let's talk about a different example, another example in this case. We would have a step function. Let's define that step function to be composed of two parts. It gives me the value of 1 when x, I don't know, when x is equal to 4, and a value of 0 when x is not equal to 4, a function I just made up. It brilliantly did so. Now, let's try to plot that. So when x equals 4, so that's 1, 2, 3, 4, the value of y is 1. So that's my value of y. But what happens when x is not equal to 4? It's 4, right? When x equals 3, the value is 0. When x equals 2, the value is 0. 1, value 0. So there's basically a straight line that's forming over here, right? But at x equals 4, it's discontinuous, which means that this graph is like being drawn on this line, and when it reaches 4, it just jumps over here. It makes that jump. And then when it moves to 4.00001, which is basically the next value, right? Whatever that is, it just drops back in and continues. So what you're seeing is this. That jump over here, and then it just carries on its way. So what you're seeing over here is discontinuity. This graph exists. That's for x is not equal to 4, and that's for x equals 4. So there appears to be discontinuity over here. Let's try to evaluate the limit. Or basically, let's try to evaluate continuity. So if we apply the first rule, does f of 4 exist? Because we're approaching 4, right? We're trying to find continuity at 4. And continuity, by the way, is determined at points. And if it's valid for all points, then the function is continuous for all points. But let's just talk about one point. Does f of 4 exist? Well, when x equals 4, f of 4 does exist. It equals 1. Let's talk about the second condition. What happens when limit of x approaches 4 for the function f of x? Well, we know that when x is trying to approach 4, x is not equal to 4. It's very close to 4, but it's not equal to 4, which means which function are we going to use now? 1 or 0? Think about it, right? We're going to use 0 because x approaches 4, but it's not equal to 4, which means the value of x, as we're trying to get closer and closer to 4, is 0. We get very close to 4, but we can't make that a jump because we never equal 4, which means this is going to be 0 now. We're going to choose this. And the third condition, because now we've met the first two, does the function value equal the limit value? Does the function value equal limit value? Well, 1 does not equal 0, hence 3 fails. So the function is not continuous at 4. X equals 4. The next video, we're going to try to explore these concepts in further detail, maybe talk about some more examples or some rules that are applicable to all continuous functions. See you guys in the next video.